We're now recording. So, a reminder, horizontal projection, always we're at this point and we go off a cliff, yeah? That's horizontal projection, horo-proj. Don't forget about this, okay? And then we tend to, most cases we're dealing, you right, Nicola? Okay. You dropped it, did you? In most cases, we're imagining situations here where we're falling through the air after being projected horizontally, okay? Important that we recognize here that there is no initial component of velocity. That's a key thing about horizontal projection. That all changes when we do projection at an angle, proj at theta. This is the case we're describing. We have some initial velocity, and that initial velocity has some angle. So we go like this, before we strike the ground. Okay. Now, within projection at an angle, there are actually 3 different cases. The simplest case is the one you see there. We're going to refer to that one as case 2, though, I think because that's what your textbook does. And I want you guys to be able to refer to your textbook, so we'll keep it the same. Yeah, so they call this one case 1. So 3 cases here. We're going to do 3 columns. We're going to look at a quick diagram of each one and explain the key differences. Case 1, case 2, and case 3. Proj at theta. Yeah, I know, just to be annoying and really lazy. Your thetas are bad. Wow. Oops, guys, you're hurting my feelings. Theta. Better? Happy now? You know what it looks like? Saturn. Exactly what Saturn looks like. All right, case 1. Landing at launch height. That's a U, that's an N. Nice flat line. Point of projection. Point of landing. Simplest case. Perfectly symmetrical. Quite easy to deal with. It's actually, in a weird sort of world, if you could reverse time, just 2 different projections at off a cliff. Horizontal projection problems. If we imagine up here, that's where we started. We go that way, and we fall due to gravity, just like we do in horizontal projection. Or we could go that way if we were initially thrown that way, and it would trace in time and space exactly the same. Case 2 is landing, I think your textbook does higher. No, landing lower. Landing lower than launch height. So it's this case. Some U at an angle. I won't even draw the notation actually. And then dropping down and landing just like we did with a lot of the horizontal projection. Down here, some displacement. So we have actually got in these problems an SY. In this case, our SY generally is imagined at that point, the maximum height. Because like I said, we split this problem symmetrically in half. So often we talk about SY. Now, SY is whatever the hell you want it to be. Let's not forget that. It's a relative term, okay? If you want to imagine the height of this ball a second before it hits the ground, you can do that. You just use all the values that associate with that time, okay? If you know this is in the air for 6 seconds before it lands, and they say find its displacement a second before it hits the ground, then you just use time equals 5. And you can do all the math to work that out with a displacement from there to there. It doesn't matter. It's all relative, okay? Important to recognize that. All right, and this last one obviously is landing above launch height. So this is the old basketball hoop example. Okay? What? Projectile motion in a circle we'll do later. It's circular motion. And yeah, where it ends is where it starts. It's called a period. Now in this one again, you have an SY generally from the difference between the launch height and the landing height, of course. That's generally what we'll refer to as SY. But again, it can be whatever the hell we want it to be. You could be asked the height above the ground at the maximum height of the ball, where VY, the velocity in the Y direction is 0. Remember, maximum height, Y velocity becomes 0 for a moment. And then it becomes negative again, okay? Now, as a rule of practice, generally try to adhere to positive up, negative down, and consider whether the ball is moving up or down, okay? In this case, the overall displacement at the point of landing in the Y direction is 0, right? Where it lands, its displacement is 0 in the Y direction. Obviously, it's moved horizontally, but we could ask for the maximum height, and we often do. Okay, some key features about this. What can we identify here? We can identify that yeah, maybe we just jump into examples of these. I think that might be better. Yes, through an example. Okay, no, there are a couple of key features that are worth mentioning, I guess. Uy is equal to negative Vy. Okay, think about that. Uy is equal to negative Vy. If this is Uy, maybe I'll use some color to refer to this. Uy Vy. Right, do you see what I mean by this? Uy is going to be the negative Vy. Now, again, that's only relative to where we're talking about. If we're talking about the final velocity as being the point where we're at the maximum displacement, that's not the case. Vy is 0. Okay? This is only the case when we're talking about this and this. The initial velocity in the positive direction is exactly the same as the final velocity in the negative direction. Okay? Obviously here, in this case, Vy in the final direction here is going to be much greater, right? But it's commonly the case that Sy is negative. Whereas here, Sy is commonly positive. Okay? And I think that's really it. So then we'll just talk about how to solve them. Which again, the process is going to be no different now from horizontal projection. We are going to look at an example of each. We're going to identify the information we're given and the formulas that will help us. It's the exact same formulas as horizontal projection. Some other ones might come up, okay? So let's go to that now. We'll do example 1, example 2, and example 3. Yes, Alex. Is it? 200 meters every second. Okay, example 1 looks like that. Example 2. That says cliff. Example 2 for you. Wasn't my best work. Here's my beautiful artwork. All right, ton of assumptions in that last one. Yeah, ton of assumptions that we can make. Right angles, things like that. Please make them. Otherwise, you'll have a hard time solving these. All right. So those are our three different scenarios that we can imagine. Again, the formulas and the math is going to be the same. The key difference is in the first one, things are symmetrical either side of that maximum height. In the second one, they are not. Okay, that really changes things for us. Okay. In the first one, any time of flight, you can just halve it and you get the time that the ball is at maximum height. In the second and third ones, you can't do that. In the first one, any horizontal displacement, you can just halve it and you find the displacement at the maximum height. Second and third ones, you can't. Okay? But nonetheless, with all three of these, we always know that max height occurs when the velocity is 0. So let's get started. I'm going to do example 1, and then we're probably going to well and truly run out of time. We have next lesson single to spend on this, but then we're done. Okay. Now, as far as chapter 1 review is going, that was going to be due on Thursday. That might be a bit unfair to ask, considering that we won't have actually done the whole chapter before Tuesday. Sorry, tomorrow, not Wednesday. So I might extend that for one more week. Okay. All right. So let's do this first one here. And I might have to go on to the next page. I'm going to struggle to find space here, but we're looking for ux and uy. We very clearly know what u is, right? That's u. So we know that ux is going to be the horizontal component, ui the vertical component. This is just vectors in component form. We also know that that's 40 degrees. So sine theta equals O over H. Sine of 40 times by U equals O. Check, you know where I did that? Oh, and I'll write that O is UI, equals UI. So UI is just sine 40 times by U. Make sure you know where everything there came from. Therefore, UI, 129. It's pretty obvious in this problem and most of these, but it can be worth noting that that's positive, so up. Ux, of course, is going to be just cos, exact same thing. So Ux is equal to U cos theta. Positive, so to the right. Again, arbitrary, set by us. Okay, are we pretty comfortable with the component form of vectors by now? Is it okay that I've totally left out a ton of steps there? I haven't shown you the substitution of the numbers. We haven't talked about the powers or anything. Sorry, not powers, the signs or anything like that. That's fine with everyone? Now, I'm going to skip ahead to the next page and continue on with example 1, and then we'll come back to example 2. We'll start that on this page and go to the next page and do that. Is that okay with everyone? All right, is anyone still copying these examples down? No? Okay. Keep talking to me, guys. You're going a bit quiet on me. After I look at example 1, you want to do what? Oh, right. In real life. Sure. Example 1, example 2, example 3. So let's do B now, which was time of flight, was it? Thank you. Obviously, you can watch this, Tanika. Obviously, you can watch this on YouTube just for the last part if you want to catch it, and then get the notes off the learning place. Thank you. Sorry, B was maximum height. Max height. What do we know about max height? Let's call it S max. Why? Toby? Keeping up with me? Actually, yeah. Good. All I care about. Also bullying a classmate. But anyway, S max Y, we're going to call it, not just SY, because that generally refers to that overall displacement. So this is an easy way to identify that we're talking about that maximum. When, and I'm going to say it like this, when S, I've done a bad job of it, but when S equals, when SY equals S max Y, what do we know? Vy equals 0. Okay, we know that for a fact. So how do we find SY when Vy equals 0? What formula is it? Vy squared equals 2GSY plus Uy squared. This is exactly the same, Uy squared? Yeah? This is exactly the same as the one we did for horizontal projection. Yeah, I was going to say, no, that's a different one. The T is a different one. Yeah, that's the second formula. This is exactly the same problem as before, except for one important difference. Before, the U could just cancel out to a 0. This time it can't. We have to know that value. Thankfully, we just did it on the previous page, the Y component of the initial velocity. Okay, so let's sub in values. We're trying to find, we know Vy is 0, so that's 0 equals 2. We know that gravity is negative 9.8. We don't know what Sy is. We're trying to solve for that. We know that Uy is what? What was our Uy from the previous page? 129? Yep, 129 plus 129 squared. Now we can rearrange. We're going to have Sy equals, so what do? We got to do minus 129 squared, which let's quickly calculate that. 16,641. As a negative. Take that over. Divide by 2 times negative 9.8, or divide by negative 19.6. And that's it. If you do an analysis of the units here too, you'll see the units work out. You do just cancel out to have just meters, so that's great. We end up with, what was it, Alex? 849 meters. Seems about right, yep. Take that in, absorb that, we'll leave that there, we'll come back to those examples later. Please try and keep those 3 columns nice and clear as we go through case 1, case 2, case 3, example 1, example 2, example 3. We will resume from here on Wednesday. What's up? All right, I'll leave that up for you guys to get your notes down and